So in this part we'll now prove the converses, and this isn't actually too arduous at all. We'll do this by contradiction, and we'll be able to use the two things that we've already proven to make the proof of these two things very quick. So we'll begin with this first one that I've underlined in blue here. Now before we begin the proof by contradiction, I just want to go over what this theorem says again, because there is a potential for a misunderstanding here. So this theorem says that if you have a stationary point at x0, so the derivative at x0 exists and it's equal to 0, and you know that at that stationary point the function has a local minimum, and you know that the second derivative exists at that point, then you can conclude that the second derivative at x0 must be greater than or equal to 0. That's the place where you could misunderstand this. It's important that one of our initial assumptions is that the second derivative does exist. The theorem isn't that if you have this stationary point that is a local minimum, then the second derivative exists and it is greater than or equal to 0. No, it doesn't show that the second derivative exists. If the second derivative exists, i.e. it's an assumption of the theorem, then you can conclude with this other information that it's a local minimum and that it's a stationary point, that the second derivative must be greater than or equal to 0. And similarly for this one, if you have a stationary point that is a local maximum and the second derivative exists at that stationary point, then you can conclude that the second derivative at that point is less than or equal to 0. So our initial assumptions then for this proof by contradiction are that x0 is a stationary point, that it is a local minimum, and that the second derivative exists there. So we're now going to assume the opposite of the result is true and derive a contradiction. So the opposite of the second derivative being greater than or equal to 0 is that the second derivative at x0 is strictly less than 0. So we'll assume this and we'll derive a contradiction. So this is pretty immediate from what we've already shown. So we've already shown that if you have a stationary point where the second derivative exists and it is less than 0, you can conclude that that point x0 is a local maximum. So if this is true, we can conclude that it's a local maximum, which of course is contradictory to one of our starting assumptions, which is that it is a local minimum. So I've written this consequence out here. So from the fact that the second derivative at x0 is less than 0, from what we've already shown, we can conclude that the function has a local maximum at x0, i.e. that there exists some interval around x0, I've called it a delta interval, so an interval from x0 minus delta to x0 plus delta, such that if you take anything inside that interval, so any x that's in that interval, except of course x0 itself, so subtract off x0 itself from this set, then if you look at what f of x is, it is strictly less than f of x0. That's what it means for x0 to be a local maximum. But this contradicts the definition of local minimum possibly being true. You see, if x0 was a local minimum, then there would have to exist an interval around x0, we'll call this an epsilon interval, such that if you take any x inside this epsilon interval from x0 minus epsilon to x0 plus epsilon, except x0 itself, then if you look at what f of x is, it has to be strictly greater than f of x0. But these two things aren't compatible with one another. This one blocks this from being true, because whatever epsilon you take, it's always going to have to contain at least part of this delta interval. So for example, if you make epsilon bigger than delta, or bigger than or equal to delta, then this entire interval will be contained inside this epsilon interval. So this certainly isn't going to be true for all x inside this, because all of the things that are inside this part of the delta interval that's not x0 are going to obey the exact opposite thing. On the other hand, if you make epsilon smaller than delta, you're still going to always contain part of this delta interval here. So epsilon, remember, has to be greater than 0, so this is never just going to be the set containing x0 by itself. Epsilon always has to be greater than 0. So you're always going to get a little bit of this delta interval, and for those points that are inside that delta interval, they're going to obey this, which is the opposite of this. So you cannot possibly have an epsilon interval on which this is true if you've got this delta interval on which this is true. They are not compatible with one another, so this is a contradiction. Hence, if you have a stationary point which is a local minimum where the second derivative exists, it cannot be the case that the second derivative at that point is less than 0. Therefore, not this must be true, and not this. The logical negation of this is that the second derivative at x0 is greater than or equal to 0, and hence we can conclude that this first one is true. And it's the exact same argument for this second one that I've underlined in green now. So if we have a stationary point at x0 and we assume that that stationary point is a local maximum and we assume that the second derivative exists at that point, then you can conclude that the second derivative at that point must be less than or equal to 0, and the proof of that is by contradiction. So we assume the opposite of this, which is that the second derivative at x0 is strictly greater than 0, and we derive a contradiction from that. And quite simply, we just go up to this result this time. We have a stationary point where the second derivative exists, and we're assuming its value is greater than 0, hence from point 1 that we proved, we can conclude that x0 is a local minimum, but that contradicts it being a local maximum for the same argument as we've had here. Just to go over that argument again, and I'll do it a little bit more pictorially this time, if we know that x0 is a local minimum, then there must exist a delta interval around x0, which I've drawn here, x0 minus delta to x0 plus delta, such that all the things inside this interval, bar the centrepiece itself, if you look at what they're mapped onto, so f of x, it's going to be greater than f of x0. That's the meaning of x0 being a local minimum. But that contradicts it being a local maximum. Because if it's a local maximum, there must exist an epsilon interval around x0, which I'm showing in red here, such that if you take any point in the epsilon interval apart from x0 itself and look at what it's mapped onto, f of x is going to be less than f of x0. That's the meaning of x0 being a local maximum. And whatever you make that epsilon, and I've shown two different epsilon intervals here, one where epsilon is bigger than the delta, and one where the epsilon is smaller than the delta, you can see that you're always going to get part of this delta interval contained in your epsilon interval. And given that these things are opposites of one another, this cannot be true for all the points in the epsilon interval because it's containing points in the delta interval where the absolute opposite is true. So you can therefore conclude that if you have a stationary point which is a local maximum and the second derivative exists, that this cannot be true, that the second derivative is greater than 0, therefore not this is true, which is that the second derivative is less than or equal to 0. And with that we're finished, so we will end there. Thank you for watching.